Okay, we'd like to thank everybody for tuning in. We're going to go ahead and get started now. For those of you here in the room, please take your seats. This is the research results presentation for linking land use and travel in Ohio, a study conducted by Dr. Gulsha Akkar of The Ohio State University. Her and her co-PI, Dr. Stephen Gordon, are here to give the results presentation. For those of you who are watching on the webcast, if you have any questions during the webinar, please email those to research@dot.state.oh.us, and we will relay those to the presenters for them to answer. Those of you here in the room, if you have questions, please hold them till the end of the presentation. The presentation today is being recorded and will be available on the research website in a couple of weeks, along with a PDF version of the slides. The final report on this project is also right now being published and will also be available on the research website in the next few weeks. With that, Dr. Akkar.
Okay. Well, thanks for the introduction. As Vicky said, my name is Gulsha Akkar, and I'm an assistant professor at the Ohio State University, City and Regional Planning. We have Professor Gordon here and Yuan here. So Professor Gordon and Yuan are here from the Ohio Supercomputer Center. And we're going to be presenting together. So I will start first, and then Professor Gordon will take over. So as we all know, the links between transportation demand, urban form, the distribution of employment and population has been studied by several researchers. In this research, we took a similar approach. We took a similar focus, and we focused on the links between transportation infrastructure, land allocation, and the resulting travel patterns, specifically for the state of Ohio. And the motivation for this study was to develop a user-friendly modeling tool to enable the decision makers to understand the implications of different scenarios, different allocations of population and employment distribution. We started with the land allocation model that was developed by MORPC and enhanced that model. And we also added a transportation component to this model. In this research study, we looked at the household travel only. The reason for that is over 3/4 of the vehicle miles traveled on our nation's highways are due to household travel. And the resulting carbon footprint of daily travel depends on the types of vehicles the households own, the fuel efficiency, and the number of miles traveled. So in this research project, we are focusing on the third one, the number of miles traveled. And so several researchers agree that although there are technological innovations that will decrease the fuel consumption and increase the efficiency of the vehicles, that these technological innovations alone will not be enough to get to the targeted reductions in carbon, in greenhouse gas emissions, because vehicle miles traveled, the increases in vehicle miles traveled will outpace those innovations. So there is a clear understanding that we need to understand the determinants of vehicle miles traveled and understand the implications of different land use, land allocation scenarios. So the tool that we developed for this study has two main components, the transportation component and the land allocation component. I'm going to be talking more on the transportation component, and then Professor Gordon is going to take over and talk about the land allocation component. So what the model does is it takes as inputs the future population and employment forecasts. Oh, okay. So what the model does is it takes into account the environmental constraints, where available, the future forecasts for employment and population, and then gives the distribution of population and employment. And the transportation component takes them as inputs and forecasts the number of auto trips and auto trip distances. And with those, we can get to the vehicle miles traveled at the TAZ level. So the transportation component aims to answer three main questions. Given a distribution of population and employment scenario, how many auto trips will be generated, what will be the average trip length, and what will be the resulting vehicle miles traveled. So to develop these models, we use data from several different sources. Some of them came from Ohio Department of Transportation. We used the household travel surveys that were conducted by the Ohio Department of Transportation. We used information from census and also information from several transit agencies regarding transit availability at the traffic analysis zones. We developed two main models. One is the auto trip ends at the TAZ level, and the second one is the auto trip distances at the TAZ level. So this is a figure that shows how the transportation component works. So the inputs are on the left side, the transit information from the transit agencies in terms of whether there is transit availability in the TAZ or not. The outputs of the land allocation model, the distribution of employment and households, and household characteristics from census data. They are inputs to the auto trip ends model and the trip distance model. And together, these models, when we know the number of auto trips and the average trip distances, these two give us the vehicle miles traveled at the TAZ level. So before I go into the details about the models, I just want to give you a little bit of a background about how we are traveling at Ohio. So not surprisingly, over 90% of the trips are made by our auto trips across the metropolitan regions of Ohio. And looking at the auto trip ends, we see that Cleveland and Mid-Ohio regions are the ones which are producing the highest auto trip ends. And the average trip length across the state is around 7.8 miles, and we see the longest trip distances across the non-metropolitan areas. So I will start with the auto trip ends model. To estimate the auto trip rates at the TAZ level, we got the auto trip ends which are the outputs of the statewide travel demand model. And the statewide travel demand model was run by MORPC, by our collaborators from MORPC. And we use this as the dependent variable, and it's regressed against 4 different types of employment and number of households. Also, to account for transit availability, we created a binary variable which takes on a value of 1 if there's transit stops available in the TAZ or within half a mile of the center of the TAZ. And we created interaction terms with number of households and employment and this transit variable. So looking at the results, one more thing. We forced the intercept of the regression to be 0 so that the TAZs with no households or no employment wouldn't create any trips, or there won't be any negative trip ends. So looking at this results table, the ones with green are statistically significant and they increase the number of trip ends, and the ones in red are which are statistically significant and they decrease the number of trip ends. So each employment category and number of households, they are creating auto trip ends. And if there is transit availability, there is a correction term. The interaction term will reduce the number of auto trips. So for instance, each retail employment will create 9.5 auto trip ends. And if there is transit availability in that TAZ, then there will be a reduction of 2 trip ends for that TAZ. So this is the auto trip ends model for the metropolitan areas. And then we have a second one for the non-metropolitan areas. The non-metropolitan areas do not have any transit, so the transit interaction variables are simply dropped. And we see some changes in the coefficients. If you paid attention, you would see that the model fits for both the metropolitan areas and the non-metropolitan areas are quite high. So the explanatory power, the prediction power of these models are quite high. So if you look at the observed auto trip ends and estimated auto trip ends side by side across Ohio, we see that the explanatory power, the prediction power of the models are quite high. So they're almost similar. The second model, the second transportation model, is the trip distance model at the TAZ level. And for this model, we use the logarithm of the average trip distance at the TAZ level as a dependent variable. And we try to explain this as a function of TAZ characteristics in terms of employment and households, household characteristics at the TAZ level, and the job household index within 20-minute travel time of the TAZ. So the index takes on a value of 0 if there is only households or if there is only employment present. And it takes on a value of 1 if there is a perfect balance where there is one job for each household within 20-minute travel time. So 0 means there is no balance, there is only employment or only households, and 1, as it increases towards 1, there is one job per household. So looking at the distance model, again, the green ones increase the dependent variable, and the red ones decrease the dependent variable, which is the trip distance. The findings are generally consistent with the literature. We see that as the vehicles per household driver increases, the trip distances increase. Retail and household density, they both decrease the trip distances. And the job household index, as it increases, which means as there is more balance between households and jobs, the trip distances decreases. So the R-squared, the model fit for this model is not as good as the auto trip ends model. But the literature, if you look at the literature, this is not dissimilar from other studies in the transportation field. So looking at these models in general, I talked about the model fit. The explanatory power of the auto trip ends model is quite high, and there are auto trips associated with each type of employment and households. And the transit availability affects the number of auto trips that are generated. The effect of transit availability is different for different employment types, and we see the highest impact for retail employment. And the outputs of the land allocation model are actually the inputs for this model. The household density, the density of retail employment, or the number of different employment categories are taken from the land allocation model. So once we have the results of these two models, the auto trips at the TAZ level and the trip distances at the TAZ level, if you know the number and the average distance, then we can easily calculate the vehicle miles traveled at the TAZ level. So with this, I will pass the presentation to Professor Gordon, and he's going to talk about the land allocation component of the model. Do you want this? It's on.
I want to turn it off.
Oh, okay.
So I want to make sure this mic is on. Is everything working back there? Okay. So the original model we got from the Mid-Ohio Regional Planning Commission, they had divided the region into 40-acre cells and then used a scoring system for each of those cells to decide what would be the likelihood of land use development in the future. So there were a number of factors that affected those scores, which I'll talk about in a minute. And then the growth was capped by a regional forecast for both employment and households into those 4 employment categories that Gulsha already talked about. So in order to do this for the rest of the state, our first job was to try to compile a similar set of data from publicly available sources. So Mid-Ohio Regional Planning Commission expended quite a lot of effort to get detailed data at the 40-acre cells. And we weren't able to match that at the statewide level. But what we were able to do was come up with the main categories of things to demonstrate that this is possible. And, of course, the model could be improved in the future as we get better data at that level. So we divided each of the regions into 40-acre cells for all the major metropolitan areas in the state. We calculated and assigned the values to the cells based on the available data, and that became the basis for starting our land allocation models. Just to give you an idea of the factors without going into great detail, there are really several sets of positive and negative factors which were thought to influence land use allocation. So the first set were economic development factors. If the areas were in various kinds of zones that had incentives for economic development, whether those were tax related or other kinds of services, then that created a higher score for that cell to be developed in the future. The second set had to do with infrastructure availability, right? Water and sewer services, accessibility of the transit, transportation services, both transit and roads, right? All of those things affecting it as positive things. And again, if those were available in a higher level relative to the criteria, then that cell got a higher score. Then there were several sets of things which limited or decreased the score. So environmental factors were those. So if it was located near some sort of a facility that was thought to be disruptive, right? So a noisy factory, landfill, a wastewater treatment plant, or in some sort of conservation area, very high slopes, or put into preservation, right, as a state park or federal lands or something like that, then that would make it less likely to develop. And finally, there were nuisance limitations, things like airports and quarries and other kinds of things that were also negative factors. And so to the extent possible, we put that material together for all the metropolitan areas of the state. So the general flow chart here is fairly complicated. This is more in line with the original model. And I just want to give you a general idea of what how the model works. And so the projection is to the year 2035 with a base year of 2000, because that's where most of the data were available for all the trip models that Gulsha talked about. So we use that as the base. Basically, in the original model, based on the score, the higher the score, the higher the likelihood that a cell would develop. And in the original MORPSI version of the model, what happened was they allocated portions of the projected regional development to the cells with the highest score, but they dampened it in terms of it's not all going to happen overnight, so they sort of slowed development down, so it never got to what they defined as the full built capacity of each cell. And that full built capacity is dependent on what future land use that cell was assigned. So each future land use had a particular density associated with it, and therefore that was its full built capacity. So once that was done, what happened is you ended up at the bottom here with the allocations of households and employment in each of the cells, which is what we needed for the input to the transportation model. And then in post-processing, you could do things like look at the patterns and those kinds of things. Now, what we decided initially was that although we are all wonderful planners, that things don't always go as planned. And what we wanted to do in the model was to actually add some randomness, right? Because some things come along, right? A developer comes along and wants to do something, and it has nothing to do with the local zoning, but they have some political clout, and all of a sudden something gets built there that wasn't expected and wasn't on the zoning map. And so we wanted to introduce that sort of randomness to the model, and so we did that. And so what we did was convert the scores into probabilities. So the higher the score, the higher probability of development, but it didn't mean that a cell couldn't be developed. And so we included a random process, and this random process then takes a cell at random and looks at its probability of development, and then it takes another random number, and if that random number is less than or equal to the score, the probability, then it develops. So it's less likely to develop, but it means that some odd development will take place, right, that wasn't expected because of these random events. And we think that that gives a more realistic view of what actually happens in terms of land use change as we go forward, this sort of Monte Carlo. So that was our first thing, and that we thought gave a little bit less deterministic view of land use change, which may be a little bit more realistic. The second thing we discovered is that, or we didn't discover it, everybody sort of knows that except for the Mid-Ohio region, that most of the rest of the state has portions of counties or municipalities that are actually in decline. They're not in growth. And so we had to come up with a way of forecasting what that decline might be and what the balance was between growth and decline, because in the same region we'd have portions of the region that would grow and other portions that would be in steep decline. And I'll show you a map that sort of illustrates that as an example. And so what we did to do that is we analyzed two sets of data. We analyzed population data down to the census block level using the 2000 and 2010 census to look at growth and decline across the state at that level. And then we assigned scores to the cells from -3 through 0 to +3 to represent the range, the amount of decline or growth, where -3 would be the most decline, 0 would be almost neutral, a little bit of growth, a little bit of decline, and +3 would be a lot of growth, right? So those became the categories of our growth decline model. And we did the same thing with employment by looking at the available zip code information of employment changes at the zip code level for the years between 2004 and 2010, that those data were available, and formed a similar score related to employment at the four categories that were in the transportation model. And so these were assigned to the cells, and so we altered the model to reflect that. So, for example, here is an example in Cuyahoga County. So you can see the green on this map represents areas that are declining the most. They're in the -3 category. And so you can see in the central part of Cuyahoga County, Cleveland particularly, but also some places out in Lorain and a few others have been in fairly steep decline, right? The yellow represents the sort of the neutral category, and the orange and red represents some growth. So you can see that there's sort of a mix of growth and decline. And then this is a typical pattern of all the other metro areas in Ohio, where there are some areas of growth and decline, and they vary differently by category. So if you look at retail jobs, it'll be a different map than industrial or so on. So we have a score for each of those categories that reflects these changes, and that affects how the cells develop as we do the land allocation model in the future. So when we put these two things together, we now have a bifurcated model where in the first step what we have to decide is we choose a cell, and now we have to decide, is this cell going to grow or decline? And so depending on its score, we decide whether or not it's going to grow or decline. Right? And once it's assigned to grow or decline in the first time period, it stays in that category for the entire time period, for the entire run, so to speak. All right, so we have a set of cells that are growing, and we have a set of cells that are declining, and at the end what we want to end up with is the regional forecast of the total growth or decline for the region, right, by making these two things add up together. So for each of the ones that are going to grow and decline, once we select them at random, whether or not they develop is then checked against our original score. Right? If they're going to grow, then they have to have the services and all that other stuff that was in our original score in order to grow. Right? They have to have water and sewer and all of that. So we go back to that idea to decide whether it's going to grow. It doesn't matter whether it has services if it declines. Right? And so that's how the model now gets reflected to the other regions of Ohio where we do have this mix of growth and decline. Okay? So this is the second part of this flow chart. Again, I don't want to get into detail, but this sort of shows step by step what happens. And if you have detailed questions at the end, I'll be glad to go back and go through this. But I don't want to bore you with every step of the program, so to speak. Okay? So when we did this, what did this give us? What this allowed us to do when we got done with the run was to sum the households and jobs by category at the TAZ level. and use those then to forecast the transportation impacts. And we did that using a number of different scenarios, which I'll talk about in a minute. But what we're trying to define is trip ends, and we did trip ends assuming that nothing changes in the transit, right? And then we did another scenario, which I'll talk about, where we assume that some additional transit was added, just to see what those differences were, although those are modest. And we also then were able to forecast trip length and then put those two together to forecast the vehicle miles traveled. So the outputs of the scenarios are the actual allocations of households and jobs by category, and then those are used in a secondary step to forecast the trips generated and the VMT. In order to demonstrate the usefulness of this to sort of look at alternative futures for portions of the state, we looked at 4 major scenarios. So scenario 1 is saying, let's take the regional forecast, which is based on historic trends for each region. So some regions are declining and some are growing, right? And let's see what happens if we don't change anything. We're not changing any of the physical facilities. We're just, this is where they're available, and this is what happens under scenario 1. So it's a continuation of current trends. It's sort of business as usual. You might think of it as that way. Scenario 2 is somewhat different. Here what we did is we got a couple of case studies from ODOT of major employment sites that might get developed in the short run. And the question is, can we then use our model to look at what happens in the neighborhood of those sites to the trips? And so I'll talk about that a little bit. Scenario 3, what we try to do is think about what the future might hold. And you think about some current trends, and you know that you may have noticed that there is some movement back towards central cities, right away from far suburbs, as gasoline prices go up and people are less willing to travel. Plus the changes in the housing market are also tending to push fewer people into single-family homes and more into multifamily. And so we said, okay, so what if that happens, right? What if there's development at higher densities, right, back into the central city and away from the suburban sprawl that's been in the past? What does that do in terms of changing the patterns of travel? And then the last scenario is taking scenario 3 impacts and saying, along with that increased density development, what if those areas that are redeveloping at higher density also get transit if they didn't have it before? Okay? So this is a way of demonstrating various ways the model can be used to do these kinds of policy forecasts. So here's an example from Central Ohio. What we chose was places that had high scores for household development. And we said, instead of developing them at the densities that were originally forecast and originally zoned for, what if we developed them at higher density instead? And so that resulted in these cells being selected, and you can see in the Central Ohio region, they were mostly in Franklin County, right, and mostly in the central city or the core of some of our satellite cities. Okay, so that's an example. So we did this again. This is an example, and we could put you to sleep with thousands of maps, right, of each scenario and each thing. But I just wanted to show some examples. So this is sort of what happens to the pattern in Columbus as an example. And it shows the changes in VMT in this forecast period between the base case, where things were business as usual, in this higher density case. And what this does is reduces the VMT by a fairly substantial amount, 1.9 million vehicle miles traveled. So what this illustrates is if that trend were to continue, right, or to happen, right, that we have higher density development of residential, we would expect major changes in travel patterns in the region as a result. This is just looking at the same thing in terms of data distributed across household and jobs between the base case and the 2000 and what happens over the 35-year forecast period. So in Mid-Ohio, what's forecast is a 25 to 30% growth continuing past trends, and that's sort of what we're simulating here as our control totals. And it shows, just in summary, that the vehicle miles traveled under this base case goes from about 27 million to 37 million, so an increase of 10 million VMT if we keep going with sprawl, right? That's sort of what it shows. This is the base case versus scenario 3 showing the reduction. So we go from that 37 million down to about 35.5 million. That's our reduction of 1.9 million I showed you on that other map. There were two sites that we were able to do the site-specific kind of analysis from. One was a site in Toledo, I think where the old Jeep plant is, and that may be redeveloped. So we took the number of jobs forecast for that site and looked at two things. We looked at what happens to vehicle miles traveled from the site altogether, and in the three TAZs that are overlap with the site, and then what happens in the surrounding TAZs as a result of that, given our model. And you can see that we add about 4,800 VMT, or 973 trips per day because of this. But it actually, because of the increase in employment, it actually cuts down on the distance traveled because in those adjacent sites, because they are now getting to employment easier. So that sort of shows the interrelationship between the trip distance and the trip generation model there. The second site was the Rickenbacker, further development of the Rickenbacker site in central Ohio, and the numbers we've given generate about almost 16,000 new trips, and you can see the distribution there. So this would be one quick way to do a sort of a quickie assessment. It's not obviously at the same level of detail as a traffic study, but if one is looking at major redevelopments, this is a quickie way of getting sort of an estimate of how many new trips might be generated that you then have to worry about whether you have the infrastructure to handle, right? Finally, just another example of the Cleveland region. This is a comparison of the base case with my scenario 3. So the base case showed actually some decline, and so we were actually going down because of the decline in the Cleveland metropolitan region. And I reintroduced growth to Cleveland, and I hope all the people in Cleveland appreciate that. And I actually hope that it happens, right? But you can see that what happens when we reverse some of the trend is that we do get a modest increase in vehicle miles traveled and a slight percent change. And this was just caused by a fairly modest change in the number of cells that get redeveloped. So the model is very flexible in being able to choose those areas. Finally, in scenario 4, we took all the scenario 3 things and said the areas that are going to grow are now going to get transit if they didn't have it before. You can see that we only get a modest reduction in vehicle miles traveled, so somewhere in the neighborhood of 0.5%, something like that, and that's congruent with transit trip ends that we see in the region, right? We're just not a heavily transit state, so that's sort of why that happens. So unless there's a major shift in how we do transit, we would expect this kind of a trend for that scenario. So some related things here as we go forward in time. Of course, all of these forecasts are subject, we don't have really a better crystal ball than anybody else looking at 35 years ahead. And so the question is, will historic growth rates really occur, or will there be some reversals? There are already some things that you see in the news that may cause some reversals. So there is some onshoring of previously offshore jobs, right, coming back to areas like Ohio in selected places. There is some move towards central city redevelopment, or at least in inner suburb development, depending on where you look in the state. So as you use, if one uses a model like this, you really have to think through those questions much more carefully than probably we were able to do in the context of our study, but something that could be done. So I think as we go into the future, as we get to develop this, we may get to develop this a bit more. We'll be looking for some more guidelines which help us make more consistent forecasts of population and employment that are consistent with land use policies, different growth trends, and so on. So I'm going to turn it back to Gulsha now, and she's going to talk a little bit about some follow-on work that we have proposed for this project.
I think it's working. Okay. So as Professor... Oh, okay. I keep forgetting. So as Professor Gordon said, we would like to continue working on this model, and we have proposed some additions to our model. So we want to add 2 new components to the model. The first one is the vehicle choice component, and the second one is about the decline. So the first one, as I mentioned earlier in the presentation, one of the first few slides, the carbon footprint of household travel depends on the vehicle miles traveled, fuel efficiency of the vehicles, and the type of vehicles that the households own. So here with these models, we get at the vehicle miles traveled, but we don't have any information about the types of vehicles that are used, the fuel efficiencies, and the carbon footprints of this travel. So we would like to add a vehicle choice component to the existing model so that we can get more information about the fuel consumption and other things. The second one is about the decline, and as Professor Gordon said, even with counties with net declines or net growths, we see smaller areas which have growths, although the larger area might be declining, or vice versa. So we would like to add a decline component to our existing model so that we can better predict and forecast into the future. So in terms of the vehicle choice component, we are considering using the 2011 Cincinnati Household Travel Survey, and if any other household travel surveys become available in the meantime, we would like to also add them to our analysis. So we looked at this Cincinnati Household Travel Survey, and we see that they have information from over 5,000 households and around 5,000 vehicles, which could be linked to their vehicle miles traveled, trip distances, and so on, and the household characteristics. We would like to develop vehicle choice models either at the household level or at the TAZ level. We're going to see which one will perform better. And we would like to link the residential location characteristics and the vehicle type choice in the models. So the way that we see this, the vehicle choice component is this component can be used as a standalone model to understand the changes in the vehicle fleet corresponding to the changes in socioeconomic characteristics and land use characteristics. And it could also be integrated with the land use component to have the estimates of population and employment distribution, the resulting choices of the vehicles, people's household choices, and finally the vehicle emissions, fuel consumption, and state gas tax revenues. The choice set that we envision right now will be based on the vehicle size and function, such as small passenger cars, SUVs, pickups, minivans, and depending on the availability of the data and however many of them fall into the subgroups, we might add some subcategories like the vintage or fuel type and so on. So this is for the vehicle choice component, and Professor Gordon can talk a little bit about the decline component. Maybe you can use this. It will be more.
So essentially, in the current model, we are making sort of independent forecasts of employment and population and using that to do land allocation. But these things are not separate. And so what we want to do is actually examine more empirically the historical relationships between employment and population, so we have a more robust model. And we want to be able to not only do this to make a forecast, but we want to be able to check our forecast by sort of back forecasting using our model to see if we can actually replicate the pattern of past growth based on these new relationships. We think that that will actually improve the efficacy of the model, right, and add to its ability. So then we can connect that with future transportation fleet and possible behavior changes that Gulsha is talking about, and together then that would improve the overall model. And I believe, so just to summarize, what we hope to do if this is funded to continue is to develop this vehicle choice model to improve the land allocation model by creating a more robust model that accounts for the relationships between employment growth and decline and what happens to population, and integrate that with some other things that we can then forecast that would be of use to the state and to the local regions. We would like to acknowledge ODOT for funding the project, and particularly the people indicated here that helped us in various parts of the project. Also, Mid-Ohio Regional Planning Commission, two people there that worked with us most extensively. We had some students that helped us do some of the data gathering and analysis. And then we need to acknowledge our academic and non-academic departments, the Milton School of Architecture and the Ohio Supercomputer Center. And I think at this point, then, we are ready for questions.
Yes, we're ready for questions. If you have questions in the audience, please raise your hand. We'll bring you the mic so the people watching on the webinar can hear. If you're watching on the webinar, please email those questions to research@dot.state.oh.us. And I would like to clarify all the future work that they just spoke about is in a project that is expected to start during state fiscal year 2014. So there will be more work done on these models and more things to come. So.
Wait for the mic.
Yes, thank you. I'm curious to know, it appears obvious that none of the statistics involve southeastern Ohio, and I just wondered, is it because the sparsely populated area that it's not included here?
Yeah, we were not able to gather the same kinds of data for very rural parts of the state as we were for the metro areas. And so we just have a very general overview model, the non-metropolitan model, which we didn't really go into great detail on. But that's why, yeah. Other questions?
Can you go into what kinds of data are absolutely necessary for this to be implemented, and what kinds of data would be preferential to further refine it?
I think it's
That's
more
my
you.
So I think the absolutely necessary stuff would be I think the stuff that we already have in terms of some of the major environmental constraints and the infrastructure that's in place. I think that probably some of the data that we currently have is probably a little out of date, and so we could improve by updating that. Some of the additional stuff that we couldn't get in the short run, which might enhance the model, would be much more detailed information on things like zoning and subdivision, more detailed policies there in each of the sub areas, whether or not there are any special development districts and other things that we might have missed in publicly available data that would affect the propensity of an area to develop, those kinds of things. So those are the things that are probably missing from what we currently have, that perhaps we can get together with some of the other regional agencies and get some of that additional information. Any other questions? Yeah.
I don't mean to hog the show here. Some of you other people might. Is this thing working? Okay. I'm just curious to know, from the data and study that you've done so far, if you have any opinion, or if the data suggests one way or another, whether the probability of a mass transit system such as a train that's been recently proposed from, say, Cincinnati to Columbus to Cleveland and back, if the data suggests that a mass transit system such as that train would be a good idea or not.
Yeah, I think that's sort of beyond the scope, but we didn't really look at intercity transportation. You want to say more about that?
That's actually what I was going to say. So we didn't look at intercity transportation. So these are daily trips that people make. So not between the cities, but within their own areas. But it's something interesting to think about. So the thing is, the current data that we have, it's showing very low transit trip ends. So when we estimate the models based on those, we get very small coefficients for transit. So in the future, we might actually think about applying some other models or some other data from other regions and trying to, deal with the coefficients that way. But the model itself, as it's right now, is not going to be able to tell us anything about the transit, like the train between Columbus to Cincinnati or Cleveland, as it is right now.
Okay, you have a web question. Great presentation and great work. I'm interested in what you think about a distance to central business district variable. Let's say you start with your base land use and add a single development with a size that results in 20-minute diameter travel time. The development has even land mix, your job household index, high density, and good transit access. Compare two options dropping in this additional development right next to the central city or in farmland far away from everything. Do you think your model would estimate any difference in VMT?
So as it is right now, so if everything else is equal, it's not going to estimate anything different in VMT, but I think that's a good suggestion. So we can actually have the distance from the TAZ centroid to the nearest possible central business district in our model. So we can actually try and see if it is going to generate better trip distance models and better forecasts. I think that's a good suggestion and a good comment. So for the next generation model.
Okay, if there are no questions at this time, we will go ahead and conclude the webinar. If you do come up with questions that you would like to propose to the research team, please feel free to email those to research@dot.state.oh.us, and we will share them with Drs. Akar and Gordon to get you a response. Again, I'd like to remind you the presentation will be available in a couple of weeks along with the PowerPoint slides on the research website. Also, the final report for this project will be available in the next week or two. Thank you all very much for participating.